Atoms, despite being considered indivisible, possess unique vibrations, a fundamental characteristic of nature's building blocks. A team of researchers from the University of Washington has made a significant breakthrough by observing and utilizing this phenomenon in their recent study. Through the examination of light emitted by atoms when stimulated by a laser, they were able to detect vibrations known as atomic breathing. This breakthrough holds immense potential for advancing quantum technologies and paving the way for improved tools in various fields. Led by Mo Lee, a professor of photonics and nanodevices in the UW Department of Electrical and Computer Engineering and the UW Physics Department, the team aimed to develop an enhanced quantum emitter, QE, that could be integrated into optical circuits. QEs are essential components in the quantum technology toolkit as they facilitate the generation of individual quantum particles, known as qubits. Similar to the bits used in classical computing, qubits enable quantum computers to perform calculations that surpass the capabilities of classical computers. Typically, qubits are built using electrons or photons due to their unique quantum properties. Lee explained, "This is a new, atomic-scale platform utilizing the field of optomechanics, where light and mechanical motions are intrinsically coupled together. It offers a novel quantum effect that can be harnessed to control single photons traversing integrated optical circuits for numerous applications." To construct their QE, the researchers started with tungsten diselenide, a molecule composed of tungsten and selenium. They shaped it into ultra-thin sheets, each consisting of a single atom. Two of these sheets were then stacked on top of each other and placed over a series of nanopillars, each only 200 nanometers wide. This arrangement caused the sheets to deform at the points of contact, resulting in regularly spaced quantum dots. Quantum dots are semiconductor particles with unique optical and electronic properties, commonly employed in building QEs for quantum applications. Due to the deformation induced by the nanopillars, they are specifically referred to as strain-induced quantum dots. By applying a precise pulse of laser light to one of these quantum dots, an electron was dislodged from the nucleus of the tungsten diselenide atom, creating a temporary quasi-particle called an exciton. The exciton consisted of the negatively charged electron and the corresponding positively charged hole in the opposite sheet. Due to their strong bond, the electron quickly returned to the atom, releasing a single photon encoded with specific quantum information. Adina Ripon, a lead author of the paper and a doctoral student in the physics department, emphasized the importance of photons in quantum information transmission, stating, "To establish a feasible quantum network, we need reliable ways to create, manipulate, store, and transmit qubits. Photons are a natural choice for transmitting quantum information because optical fibers allow us to transport photons over long distances at high speeds, with minimal energy or information loss. This approach yielded consistent, high-quality photons suitable for potential use as qubits, which alone constituted a successful outcome. However, further analysis of the data revealed intriguing details that warranted deeper investigation. The researchers discovered the production of a quasi-particle known as a phonon during the photon creation process. Phonons are optomechanical phenomena resulting from atomic vibrations, present in all forms of matter. Phonons can be considered acoustic counterparts to photons, possessing their own quantum waveforms. While they cannot be directly seen or heard, Lee described the vibrations as the breath between atoms. In this study, the phonons were generated by the vibrations between the two atom-thin layers of tungsten diselenide, which acted like tiny drumheads resonating with each other. The team observed a tight correlation between the phonons and the emitted photons. Lee explained, "You can think of phonons as springs attached to the layers. These springs vibrate and directly influence the recombination of the exciton's electron and hole. Consequently, the emitted photon also undergoes changes." This research marked the first observation of phonons in this particular type of single photon emitter system. Additionally, when analyzing the emitted light spectrum, the team identified evenly spaced peaks representing different quantum energy levels of the phonons. Quantum theorist Ting Cao, an assistant professor in materials science and engineering, determined that each exciton-emitted photon was coupled with 1, 2, 3, or more phonons. Lee further elaborated, stating, "A phonon is the natural quantum vibration of the tungsten diselenide material, causing a vertical stretching effect on the exciton-electron-hole pair situated between the two layers. This significantly impacts the optical properties of the emitted photon by the exciton, a phenomenon previously unreported. By applying an electrical voltage to the materials, the team could manipulate the interaction between phonons, excitons, and photons. Altering the voltage allowed them to adjust the interaction energy of the associated phonons and emitted photons, offering precise control over the encoding of specific quantum information into a single photon. Ruoming Peng, another lead author of the paper who completed his doctoral degree in UWECE in 2022, expressed fascination with the discovery of this new hybrid quantum platform. He noted, "By investigating the interaction of phonons with quantum emitters, we have unveiled a realm of possibilities for controlling and manipulating quantum states. This could lead to even more exciting discoveries in the future." Lee and his team aim to expand their system further by controlling multiple emitters and their corresponding phonon states. This would enable the quantum emitters to communicate with each other, laying the foundation for novel forms of quantum circuitry. The potential applications of these approaches include quantum computing, quantum communications, and quantum sensing. The University of Washington team consists of Adina Ripin, Ruoming Peng, Xiaowei Zheng, Srivatsa Chakravarti, Minhao He, Xiaodong Xu, Kai Mei Fu, Ting Cao, and Mo Li. The research received support from the National Science Foundation, and their findings were recently published in the journal Nature Nanotechnology under the title, Tunable Phononic Coupling in Excitonic Quantum Emitters. Thanks for watching.